Hey Chemsters, it's Mrs. Bowles. Another great video. This particular one is dealing with heat and temperature and their differences and how to represent them. I have been asking you to explore this, and I want to give some detail to your process as you learn and understand it a little bit better. So let's get going on this. Whoops, I don't know what that is. There we go. So heat. As you were learning in the videos, heat is energy transferred between objects, okay? Very different than temperature. We're going to talk about that. Heat takes into account the energy transferred, the speed of the particles, as well as the quantity of the particles. Those are both included. Heat is always transferred from something warm to cool. So when you shake someone's hand, and you say, oh, they're making me cold, it's actually the opposite. They're taking away your heat. You being warmer, your energy is being transferred to a cooler person. So what about ice cubes? Ice cubes placed in water. We talk about how the ice cools down the water, and that is true, but it's actually the water removing the heat from the ice, the heat transfer from the water to the ice that melts the ice. Now, keeping in mind, temperature is a very different piece of that equation. This is the average, it's equal to the average kinetic energy of the particles in the matter that you're talking about, and it indicates how hot or how cold something is. And so, as I said, average kinetic energy or speed of the particles, it doesn't matter how many particles you have, it has to do with how fast they're traveling. Whereas heat takes into account how many of those. Expressing temperature, as you might know from your previous science classes, follows into different scales of temperature. You've probably heard of Fahrenheit. That's what we use in the US for our weather. All the other countries use Celsius, and in chemistry we use Celsius. In chemistry, we also use something called Kelvin. Kelvin is a temperature scale that has nothing below zero. In fact, zero on the Kelvin scale is called absolute zero. It's never been reached. It's a theoretical temperature at which all particle movement would stop. So notice the important things to know on these scales. Fahrenheit, freezing, 32, boiling, 212. Celsius, freezing, 0. Boiling, 100. Kelvin is very similar to Celsius, you might notice. The only difference is you add 273, and those are always positive. We use those for calculating, especially when we do math, and then that way we don't get thrown off by numbers that are going to come out to be negative. So keep in mind, when you convert from Celsius to Kelvin, you're going to add 273, to be technical, 273.15, to the Celsius to get the Kelvin. So if you want to try these two, go ahead and try them and get yourself some practice. Notice Kelvin is always higher. So if you're wondering what to do, when you have Celsius, you add to get to Kelvin. When you have Kelvin, you subtract to get to Celsius. Celsius can be negative. Kelvin can never be negative. Now I want to show you something called a heating curve. A heating curve is something pretty common that we start talking about in thermochemistry. So if we were heating some water and we started with some ice below its melting point, in other words, below zero, because you know that's the melting point, and we warmed up the ice, warmed up the ice, warmed up the ice, we would reach a time, or a temperature I should say, where it would melt. Fusion is called melting. Then we would warm it up, warm it up, warm it up in the liquid phase. Eventually, it would vaporize or boil and become a gas. So this is called a heating curve. Now, typically when I graph it in class and I plug in this specialized probe to my computer, I start with ice and I show you how as it warms up, every minute I take a reading, it's warming up, warming up, warming up, warming up. The whole time that the ice is melting, it stays at the same temperature, 0 degrees. This happened because I took the probe out. Not until all the ice melts into water do you then notice that it starts to warm up again. So this is a real live graph from class time when I'm able to do that for you in class. Now let's take a look at, I know this isn't a great picture, but it's labeled, and I want you to understand back to that same heating curve that we were just looking at. Okay, let's break that down into what is happening at each stage, because later, in fact, we could actually calculate the energy needed to take 10 grams of ice at 0 and raise them up to 25 degrees. It would require multiple steps and multiple calculations. So let me show you what some of these areas of the curve represent, and I know you can understand it. So this is a water's heating curve. On the y-axis is the temperature in Celsius. This first segment represents the solid phase, just like the one I showed you. Second segment increasing represents the liquid. The third one represents the gas. So guess what's happening here and here? I'm guessing you said at that stage it's melting. Solid turning to liquid? Correct. But something else you need to pay attention to is it's also freezing. What do you mean, Bowles? Well, at 0 degrees, which is the temperature at which this happens, if you put something in the freezer and it's cooling, it will be freezing. But if it's warming, it will be melting. And they both occur at the same exact temperature, 0 degrees. Okay? Okay, then, if you warm up the liquid after it's finally melted to 100 degrees, you can vaporize it or boil it. That's where a liquid changes to gas. Or you could also call that condensation. And remember, both of those occur at 100 degrees. So when we get into calculating, which will be a future video, you can actually calculate each segment of this curve needed to calculate this problem that was listed here. So what you would do is you would have to calculate the energy for stage 1, the energy for stage 2, 3, 4, and 5, if you wanted to know how much energy that whole thing took. And keep in mind, these are all increasing in energy or heat. I call that, as you know in the last video, endothermic. And these would all be decreasing if we were cooling, and that is known as exothermic. So I'm going to skip through these real quick, and we'll get to that in future videos. But to do this problem, you would only count this and this section representing the question that was asked. And you would calculate and you would add those up. Okay? Couple last things as we finish up with this segment. This I asked you to explore earlier. How come some materials heat up faster than others? I had you look at an experiment where ice was put on one kind of surface, wood, and another surface, metal, and what you found out was they did not respond the same. Well, that's because they have different specific heat. Specific heat is the energy that it takes to raise 1 gram of that substance 1 degree. And so specific heat is not the same for every substance. In fact, all known substances have their own specific heat that is different than every other substance. And that's why when you're at the beach, the sand always feels a lot hotter than the water, not because there's more or less of it, but because the specific heat of the sand is different than the water. Water has a very high specific heat, which means it takes a long time for it to warm up, whereas sand's specific heat is much lower and it gives you much more energy than the water does. So as we go into our next video, we're going to begin to talk about energy units and how to calculate questions that involve energy. Units for energy are joules. Now, as you know, in temperature, the units are Celsius, Fahrenheit, and Kelvin. They're different. Something you should know about energy in the form of joules is also can be calculated in something called calories. To compare that to food, though, food calories are actually 1,000 of the chemistry calories that we talk about. And for conversion purposes, 4.18 joules is equal to a calorie. Now, soon coming in our next, we'll begin to talk about how to calculate these. That's it for now.